So here we're going to have a scenario where we're releasing a rod from its initial horizontal position, and it's free to rotate, and we're going to have the angular speed when it swings through the vertical. Now we're going to do conservation of energy, because let's draw the free body diagram. Let's do energy. Let's define our system here. Because we have a change in height, we're going to talk about the rod plus the Earth. We'll include the Earth in our system, right? That's that first step if we're going to do conservation of energy. So we're going to include gravitational potential energy. And then think about the forces that are acting on it. We have gravity acting at the center of mass of the rod, and we have something that's holding it up, right? Something from the axle. Now, the mg doesn't do any work. That's the only thing's touching it, right? There's just gravity pulling on it, and then this is the only thing touching it. Nothing else is touching it during this motion. So gravity doesn't do any work because it's internal to the system, right? Because we've included the Earth in the system, so we count for it by gravitational potential energy. And then the axle doesn't move. The displacement is 0. It's external to the system, but it's not going to do any work. So the work is going to be 0, which implies that the change in energy is 0. So we're going to do conservation of energy during this motion here. Okay, so then what we're going to think about is, all right, what is the energy we start with here? And let's make our... And remember, when we're doing gravitational potential energy, you got to think about the center of mass of the object. So we're actually going to make the height 0 right down here, because that's the lowest point in the motion. You could make it down here if you want, but I like to make the lowest point of the motion because the center of mass is going from there to there. So the initial energy is we just have gravitational potential energy. Okay, so we have mgh, because it's not moving at this point, it's released from rest. Let's see, is released from, it's released. So it's assumed to be released from rest. So it only has gravitational potential energy, which is the mass times g, and the distance here is L over 2. Okay. How much energy does it have down here? Well, it has all kinetic energy. Now, does it have translational kinetic energy? No, because the axis of rotation is here, and the axis isn't moving. So it only has rotational kinetic energy, 1/2 I omega squared. Okay, and then we're just gonna, and then the I we know is 1/3 ml squared, so this will be 1/2 times 1/3 ml squared times omega squared. And by conservation of energy, because there's no change in energy, the work is 0. These are equal to each other. Okay, so then the m's cancel, and one of the l's cancel, and so you're going to get 1/6 L omega squared is going to equal 1/2 g, right? G over 2. And then omega squared will be, times 6 is going to be 3g over L. So omega is square root of 3g over L, like that.